in her brain, or an example of how it isn't. So everybody do this for me. If you don't have paper, borrow it with somebody else, from somebody else. And also with this shit, if you don't have paper. Get a piece of paper, and I'll do this with you. Right, I was born September 21st, so my birthday is coming up fast. Anybody else born September 21st? Okay, that would have tripped me out. But so what do you think are the chances that two people in here have the same birthday? What do you think about that? Huh? Pretty low, okay. Anybody else have an opinion on that? Ah, interesting. Not right, but interesting. So let's do this first. Let's do a concrete thing. Yeah. Sorry. I understand why you say that, and then we'll talk about afterwards why it's not. So I was born September 21st, so, and I also can't speak at the moment. I'm going to write the number 21 really freaking big, and maybe a couple times, so that I could read it. Can you guys in the back read that? All right. I need to be able to read your paper from where you're sitting. Everybody with me. So if you were born June 7th, put a big ass 7 on a piece of paper so I can read it. Yes? I'm not asking for the year of your birth. I'm not even asking for the month yet. I'm just asking for the day. You with me? Okay, don't show it to me yet. I'll ask you when I need to see it. I don't know why I'm showing this. Can you, real quick, just grab a blank sheet of paper, and I'll get you a copy. We're going to put the day of our birth on the piece of paper. So I was born September 21st, so I got 21. I'm going to do a little David Blank. No magic trick. Look in your wallet. Holy shit. All right. So the question is, how likely is it that two people in here have the same birthday? And sort of the consensus of the few people that spoke up is not very likely. All right. I would put money that two of us have the same birthday. And remember what I do as a profession. So I don't have a lot of that to throw around at such propositions, correct? Where are my January babies at? Hold up your numbers. So 20th, 11th, 22nd, we got kind of close there. All right, most babies are going to be in August, September, because it's 9 months after cold. February babies, where are my February? What is that? 7, okay, 7, 1, oh, okay, right there.
There you go.
February 1st, you guys. Birthday twins. Right there. And then the 11th, and you were the 7th, okay. Already, right there. I should have put money down. Damn it, that could have been. It's probably against some kind of rule to gamble with your students. So we already got one. Let's see how many. So my other class only got one pair, and that was in like November, I think. I'm starting to sweat a little bit. I always tell people, several times I've had triplets or twins, and I say, we're not going to count you. Does that make sense? Because that's an automatic, unless they were born on different years, because they're December 31st. Where am I at? January, February, March. March babies. Any March babies? Oh, you owned it. Oh, you're St. Patrick's Day?
No.
12th, okay, close. 15th, okay. Close. January, February, March, April. April babies. 28th, 2nd, 24th, 1st. I love it, another April Fool's. And then something. What does it say?
The 19th.
19th. I don't think we got a match there, right? No. February, March, April, May. 15th, 3rd. Okay. April, May, June. 8th, 16th, 15th. Oh, so close. So close. Yeah. July. July babies. 31st, 28th, 12th. Okay. August. August babies. 23rd, 22nd. Damn. September. Oh, 22nd. 28th. Is that the 9th? 14th, 11th, 2nd. Oh, man. See, what did I say about September? Okay. October. 10th. What's this say?
29th.
29th? Okay. November 21st and 7th and December. 1st? 24. Oh, look. Oh, my God. 1st. We got 2 sets of birthday twins. That kicks so much ass. Oh, 29th over there. I'm sorry. All right. Okay. So what was that? We got 2? 2. Not bad. One semester I got 5. There was only one semester that I didn't get any, but that was a lower enrolled class, which kind of makes sense. So normally, once you get past like 34 people or so in a room, it's a better than 50-50 shot. So we got about 40, well, definitely more than 34. So I felt pretty good that it was going to happen. Why? So those of you that said 1 out of 365, you would be correct if I said, do you think somebody else in here has your birthday? Right? That would be sort of the possibility then. And it wouldn't even be that. It would be related to that. So here's the problem. Here's why we don't think about this correctly. We often think about it from our own perspective. Our immediate reaction is, nobody has my birthday. What are you talking about? Right? Nobody in this room probably has my birthday. There's not that many people in here. But we also don't think about this. How many pairs of people are in here right now? And what I mean by that is, I could pair you up with her, you up with him, you up with her, you up with her, all the way through, and then I could start again with you. I could pair you. Do you understand how many pairs of people are in this room?
Yeah.
A lot. You understand? There's a lot of pairs of people. Every single pair is another chance for them to be a match. Mm-hmm. So the more chances I have, the higher the probability it's going to happen. Does that make sense? I love it. So if I only had 2 people, it's a very low chance that they're going to have the same birthday. Once you get above 34 or so, it's better than 50-50. All right? So that was not intuitive. You would not have thought that that would have happened, and it happened twice. That kicks ass. Another thing that shows you that probability is not intuitive is this thing. Let me see what you guys think about this. There's a game show called Let's Make a Deal. You guys ever heard of this game show?
Yeah.
If you're ever homesick and you just laying on the couch and maybe you watch it. It used to be hosted by Monty Hall, a guy named Monty Hall, way back in the day. So if you look this up on Google, it's going to be called the Monty Hall paradox or something, the Monty Hall problem. So it's the birthday paradox and the Monty Hall problem. Okay. So here it is. The show, people dress up silly. They have all these little games you're supposed to play. And at the end of the show, they take 3 of their big winners and they say, if you give back all your winnings, we'll let you pick a door. And behind one of the doors, there's like $50,000 or something. You with me? So behind one of the doors, there's 3 doors. And behind one of them is $50,000. And behind the other 2, at least back in the day when Jeff was a little dude staying home sick, watching this, they had goats behind the other doors. So assuming we're not there to win a goat would be bad, right? Nothing wrong with a poor little goat dude, but compared to $50,000, not a good day, right? You with me? Now, can somebody pick one of the 3 doors? I've got a winner in my mind. Pick one door.
3.
3 is what I heard first. So we got door number 3. Okay. What's the probability that the door, those of you who said 3, that door is the winner?
33.333.
Be less specific. Or actually more specific, to be honest. 1/3. 1/3 chance. Right? And we all have an understanding of the basics of probability. It's the number of things that match what we're looking for divided by the total number of things it could be. Let me say that again. Whenever I slow down, it's definitely a note. It's the number of things that match what we're looking for divided by the total number of things it could be. So the winning door, how many things could it be? 3. How many of them match what we're looking for? 1. So 1 out of 3. So we all know that. You guys know how to do basic probability. You came in knowing this. Today we're going to push that a little bit, and I'm going to claim that every single probability we calculate comes back to that idea. So I'll check in with you later after we've done some freaky probability stuff. Now, here's the trick. Yes?
Can you repeat that one last time?
Sure. Probability is the number of things that match what I'm looking for divided by the total number of things it could be. So if I had a bag of 10 marbles and 3 of them are blue, what's the probability I pick a blue marble? 3 out of 10. 3 is how many match what I'm looking for divided by the total number of things. The most basic mistake I see, I got a bag of 10 marbles, 3 of them are blue. What's the probability I pick a blue marble? The most common mistake is somebody says 1 out of 3. What is their thought process, do you think? The 3 blue, and I want to pick one of them. But do you see how that doesn't relate to the chances of doing that at all, right? I have 7 marbles that aren't blue. That should diminish the chances I pick a blue marble somehow. I've got to take that into account. Are you guys kind of with me? Okay, some of you guys didn't react to the question at all. I'm going to keep going. Yes, sorry.
So for the birthday one, would it be like 40 out of like 365 or?
So the birthday one is a little more complicated. I'm not going to devote a whole lot of time right now. And that's why I said if you want to look it up, it's called the birthday paradox. Yeah. And this is the money hall problem. All right. So on the show, you would have picked a door. You turned in all your winnings like a crazy fool. And you pick door number 3. And then the host wants to mess with your mind. The host says, okay. I'm going to open up this door, and there's a, don't laugh at my mutant goat, all right? He's had a rough life. There's my mutant, look, he's happy, all right? Leave him alone. It looks like a giant spider. I don't care. So he opens, everybody with me? You picked door number 3. The host opens door number 1 and shows you there's a goat, and then he says, do you want to switch? Do you want to switch doors? Most people will say, it doesn't matter. Those people are wrong. Mm-hmm. Yeah. The probability that you picked the right door is 1/3, correct? So 2/3 of the time, it's behind one of these other doors. The host knows everything. So why, if we picked a goat, why did the host open this door? What happens if the host opens the door with a prize? Is there any drama? Does the show continue? No, it's over. There's no drama. He's going to lose, commercial. He's going to lose people. And why would I want to put a commercial on a stupid show with no drama, right? So why would he pick this door? Because he knows there's a goat there. So listen, either we picked the prize and he could have picked either of those doors, and that's 1/3 of the time that would happen. Or we picked a goat and he opened the door that has the other goat. And how often would that happen? 2/3 of the time. So 2/3 of the time, the prize will be behind the other door. Let me go to an extreme because I can tell. I knew a lot of you guys wouldn't get it on the first go. So let's do this. We have 100 doors. 1, 2, 3, 99, 100, right? Somebody pick a number from 1 to 100. 77, I heard up here. I'm sorry, whoever said something else. Door number 77. What's the probability that that's the right door? 1 out of 100. I love it. Then the host says, okay, and you open, I'm the host, I open that door, there's a goat. I'm just going to put a G besides drawing a bunch of my little mutant goats. I open this door, there's a goat. I leave, every other door has a goat. Can you see it now? You had a 1 out of 100 chance that you picked the door with the prize. What's more likely? That you picked the door with the prize, or the host did not open this door because that's where the frickin' prize is? What's more likely? What's more likely is the prize is here, right? He's not going to open the door with the prize or else the show is over. There's no tension, there's no drama. Do you guys understand? The host has information we don't. Does that make any sense? So anybody ever heard of the show called Mythbusters? Yeah. They actually did a whole show devoted to this. They constructed a set. They did this in real time. They did a concrete experiment. And they showed that roughly twice as many times the people that switched won. And of course, we're talking about the normal setup, not the 100 doors. This one, if you switch, you increase your chances by 99 times. It's crazy. Okay, maybe. So if you think about it, you only had a 1 out of 100 chance to pick the right door. Why would he open all these doors and leave that one closed? It's more likely that has the prize. That's why he left that one closed. So there's a 99 out of 100 chance that's the prize. Because there's only a 1 out of 100 chance you just happen to pick the prize. Okay. Now, it's less important you fully understand that than you do to realize that is so counterintuitive. I think everybody would agree with me. That is very counterintuitive. Most people, when you see this problem, most people say 50-50. Yeah. Because they're not considering a person with more information than we have did something. which doesn't mean that these are now equally likely. The host knows something, and that affects why he didn't choose this door. That's why it's not 50-50. Okay, enough of it. So it's not imperative you fully understand that. What's imperative is you go into this section, into this chapter, realizing that a lot of these problems are not going to make immediate intuitive sense in terms of checking the answer, right? So very often in probability, we just have to trust the process, which does suck a little bit. Not every problem, don't get me wrong. There's going to be a lot of problems you're like, okay, that sounds about right, that sounds about right. Yeah.
But wouldn't there also be a 50-50 chance of him like doing it on purpose so they change their mind, or like doing it on purpose so they would change their mind so they would fail?
Listen, in both of these situations, he's constrained. There is either I pick the prize, which means he can open whatever of the other doors he wants to, correct? That's only a 1 out of 100 chance. Or we picked a goat, 99 out of 100 chance, and he's got to be careful about not opening the prize door. That is more likely. That is 99 times more likely. So the prize is 99 times more likely to be here. Okay, maybe? Okay. Do me a favor, just let that go a little bit. I'm sorry, go ahead. You can ask your question.
If you were on the show, you would switch?
Oh, hell yeah. If they did it like this still, then I would switch. Does that mean I would win? This is still probabilities. So what do we do with things like COVID, or things like we try to decrease the chances we get it? We wear seatbelts. Does that mean we're definitely not going to die in a car crash? No, but it decreases the chances, right? We wear condoms. Does that mean we're definitely not going to get pregnant? Get somebody pregnant, get pregnant? No, but we decrease the chances it's going to happen. Are you with me? You with me? So all we can control is the likelihood of something happening. And that's why we do it, right? But it doesn't mean that it's, so I don't want to get into this whole thing about the pandemic and certain people misunderstanding certain statistical analyses and thinking that masks don't work and blah, blah, blah. Complete and utter bullshit, but we're not going to get into that. I might have a few questions on like a test or something that actually gives you data to analyze, but I really don't want to know if anybody in here is vaccine denier, anti-vax, or whatever. You can just keep that to yourself, everybody. Okay. So. So that was just to kind of lay the groundwork of being nice to yourself in terms of trying to interpret the answer. Not every problem, because what's intuitive to us is stuff that helped us survive. So if I go this way, there's a higher chance I'm going to run into some animal that wants to eat me, so I'm going to go that way, right? That's intuitive. We don't even think about that. Yes?
This might be slightly off topic, but could you explain then why 50-50 is technically the worst chances you get? Because I've heard that many times.
Well, that doesn't make any sense. I would much rather have a 50% chance of surviving with surgery than a 4% chance of surviving with surgery. So
It just be like superstition then, because I hear that a lot. People who go to Vegas, they always say like 50-50.
oh, okay. Listen, gambler logic is very different from logic. Does that mean, do you understand? Gamblers have a very different, and it's more of a perspective thing. The math doesn't change. The interpretation of what it means changes, for damn sure. Right? So, yeah, let's not go there. I don't know if anybody in here, I'm thankfully somebody that can walk into a casino, spend a certain preset amount of money, and then walk away. Right? Thank the gods. I don't have a addiction issue or whatever. Well, I don't go to a casino very often because they're very depressing, for one thing. You see one person just sitting there just feeding this machine, smoking, and you can push a button now. You used to have to do this. At least there was a little exercise, and now it's just, and they win big, and they don't give a shit because they've lost way more than that all day. I'm sorry. It's just really depressing. You do get a lot of drinks, though, because they want to keep you from understanding what you're doing.
You can't smoke it?
What's that? You can't smoke at casinos? Oh, good. Then okay, so. Damn it. Now she's really angry. Can't even get my nicotine. All right, sorry. I'll stop. Okay. So, now I'm really forgetting what the hell I was going to do. Okay, here we go. So, I'm going to give you a situation that I like to give as a problem. And this is in the homework also. this is a beautiful situation for you guys to calculate probabilities without any formulas, right? What's the only thing I've told you so far about how to calculate a probability? The number of things that match what we're looking for divided by the total number of things it could be, right? That's all we have in terms of formulas. It's more of an idea. From our work, we're going to develop formulas. So we're not going to have a formula while we do it. We're going to figure out what the formula must be after we're done. So then a really good question you might have is, why the shit do we need the formulas? Because the situation I'm giving us is not the only possible situation, right? We will need the formulas in other situations. Is everybody semi with me? Let me just do it. Some of you guys are looking at me like I'm crazy, which I'm used to. So this is what's called a contingency table. I don't care so much about the word compared to just being able to do it. So the way this works, let me make this really big for everybody. All right. Let's say this is, let's see, people who are over 20 and people who are under 20. Let's say at least 20 up here, so that 20 is somewhere in there. Yes. Oh, let's do this. Yes. No. Let's add on one more thing. Maybe. Okay. So I ask people a question, and the answers are yes, no, maybe. Right? And I ask this question to a bunch of people, and I record their ages, so then I can break them up like this. So this is like what's called exploratory statistics. So I'm just kind of seeing, is there an apparent divide in opinions on something between these based on age? Are you kind of with me? So I'm going to make up a bunch of shit right now. 27, 5, 31, 2, 7. Okay. So how many people said yes? 39. Good. So 39 people said yes. Keep going. 29 said no. 12 said maybe. How many people are at least 20 years old?
13.
Right. 8 plus 27 plus 5, yes? How many people are under 20?
41.
Ooh, neato. I didn't even do it on purpose. All right, cool. Okay. So how many total people are represented up here? 80. Why? I get this sometimes. I appreciate most of you guys realize that would be wrong. Can you understand why somebody would do that? Somebody would put 160. They count these people and they add these people. What's wrong with what I just said? These people are these people. Yes? Does everybody see that? I almost didn't want to do this because now somebody's like, oh shit, what's the right way to do it? So a nice check is these added better be the same as these added because they're the same people, right? They're just different categories of the same person. Is everybody with me? Okay, I like it. I like it. So, let me see. Let me make sure that's on here. Now, I'm going to ask you a few probability questions. I'm going to start off nice. First question. What's the probability somebody said maybe? So what's the idea of probability? Yeah, the number that matches what we're looking for divided by the total number it could be. Yeah, so if I pick one person, let me put this down here. Pick one person. Let me help out. Pick one person. What's the probability that person said maybe? How many people could it be then? No. 80 people it could be. How many match what I'm looking for? 12. So that'll be 12 out of 80. I got 12 chances to get somebody who said maybe out of 80 total people. Does that make sense by itself? Is that cool? It's just like the 1 out of 3 you did earlier with the doors. It's exactly the same idea. Okay. What's the probability somebody is at least 20? Probably that person's at least 20.
40 out of 80?
40 out of 80. Somebody help me out, by the way. What is this as a decimal to 4 places? I want all probabilities. I want the answers to be decimals to 4 places, and then you can make it a percentage if you want to. Because I'm weird. So deal with it. 15%, 11, so 0.1500. 40 out of 80 would just be 0.5, I love it.
How'd you get to at least 20?
I was just there, at least 20.
How did you be 40? Why wouldn't it be?
How many people are at least 20 years old up here? 40, right?
What if they said no?
No. Two separate questions. What if yours says anything about no? So, tell me, guys, describe these 8 people to me. Who are these 8 people?
People who said yes about.
They said yes, and they're at least 20. Who are these people?
People who said no and are.
They said no, and they're at least 20. What about these people?
Said maybe.
They said maybe, and they're at least 20. So how many people are at least 20? I would add those up, correct, to get the whole category.
Oh, so the no and maybe lied?
Say again?
The people that said no lied?
What do you mean? So the question could be something like, did you like the last season of Game of Thrones?
Oh, okay.
Right?
That's
In which case, I would agree. If anybody said yes, they're mentally deranged. I don't know. Something's wrong. I don't know if anybody watched Game of Thrones. I start. Does that make more sense?
Yeah.
So the way to look at this is, I have a total number of people, and I broke them into different categories. That's not really what happened, because they answered my question, and then, they kind of naturally broke themselves into categories. All right? So if I give you a problem like this, I'm going to give you these numbers. The first thing you do is just make all the totals, because then that makes any probability question really easy. Okay, so let's make this a little more interesting. What's the probability that somebody said no, or they are under 20? Remember the basic idea. The number of people that match what I'm looking for divided by the total number it could be.
67 maybe.
How'd you get 67?
You add the bottom line plus the 27. 31 plus 2 plus 7 plus 27.
Okay, good. All right, I love it. So what's wrong if I do this? Let me do it wrong real quick. If I do all the under 20 people, 40, plus all the people who said no, and I get 69, what did I do wrong? So if I add all these people to all these people, what did I do wrong? I added 2, twice. I counted 2 people twice, correct? So one way I could do this, and I agree with you, that this is not the way I would do it, but if I do 40 plus 29, don't I have to subtract the 2 that I counted twice?
Yeah.
I'm going to do it that way because it relates to the general formula. But like you said, there's a smarter way to do it. Anytime I give you enough information to count, I'm just going to count. I'm not even going to use the formulas. Have I put a formula up here yet? No. We're not using formulas because I gave you everything you need to count. Smart way to do this is to go 40 under 20 people plus 27 no's I haven't counted yet. That's beautiful. And it's the same damn thing, right? What's 29 minus 2? 27. So the math didn't give a shit. Math is like, go ahead, human, do your shit. Out of what? Dear God, what's the biggest the probability could be? Or what is the decimal? So 100% or 1, correct? So do not circle that shit when you get a 117% chance. What would a 117% chance of rain mean? So much rain, it's going to be raining up from the ground and down from the sky and out from the walls, and you're like, oh, 117%. You guys understand? 100% means it's going to happen, no question. What's the lowest it could be? So obviously negatives are out. Yeah.
Also, when it says like it's like a 37% chance of rain, that means it's 100% and 37% of the area, right?
There's 2 different ways. There's at least 2 different ways that meteorologists do it. 37% chance of rain could mean that there's 37% of the area looks like it could have rain. Or 37% of the time, our models in the past ended up with rain happening, with the given situation. So, and there's more than that, to be honest. But I'm not a meteorologist, so take that with a grain of salt. And then what's that come out to be? Sorry. So that's 67 out of 80, right? Help me out, what is that?
0.8375.
8375? Does that sound good? Okay. And then you can make it 83.75% if you want to. How's everybody doing so far?
Good.
So notice this, a little example about and or. Or is the nice bouncer, and is the mean bouncer. Go with me. So I go up to a bar or nightclub or whatever, and there's a guy at the door, he's got a list. And he says to me, okay, if you want to come in, this is a mean bouncer. I came on the wrong night. It's the and bouncer. Go with me. And he says, okay, to get into this place, you gotta know Joe the bartender. I know Joe. Hey, Joe. Hey, Joe. Sweet. And he says, and you gotta be rich. Shit. And you gotta dress nice. Shit. So I'm out. I was out the minute he said and after Joe. I was out. And constricts the number of things that match. So and questions, the answer is always going to be smaller than it would have been without the and. Or questions, so if I go to the same bar the next day and it's the other bouncer, the nice bouncers, and I come up and he says, you got to be rich, damn it. Or, you got to dress nice, damn it. Or, you got to know Joe, I know Joe, I'm in. You guys with me? You guys, anybody with me? Oh my God. Okay.
Yeah.
Move head, something, okay. So, the basic idea to get from that is, the formula that we eventually make for or has got to make sense why the answer always gets bigger. The formula we end up with and, the answer should always get smaller. So we got to keep that in mind. So right here, didn't the or get bigger? Isn't that a bigger answer than no or under 20 by themselves?
Mhm.
Of course, as it let more people in. So let's try an and. What's the probability that somebody said yes and they're at least 20? So here's the trick. Has anybody ever applied for a scholarship or thinking about it? And scholarships, they very often have a list of requirements, correct? So back in my day, kids, after I finished walking uphill both ways, there was this book in the financial aid office, and I like to do this because it was literally this big. And they would give it to you, and you go to this table, and you would start reading the scholarships, and it would say, must be a math major. Check. Must have this GPA. Barely. Must blah, 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 blah. And then at the bottom it would say, must be over 12% American Indian or something. And I'm like, damn it! Next page, right? So because every single one of the statements was an and. So every statement decreased the amount of people that could get that scholarship, correct? Mm-hmm. Okay. I have to meet all the requirements when they are strung together with an and. You with me? And that's why fewer and fewer and fewer as I add to it. So, how many people meet the requirement that they said yes and they're at least 20?
8.
Beautiful. And another name for the and is intersection. Does that make sense?
Oh.
It's visually, it's kind of beautiful, right? Some of you guys might have seen this symbol before. I don't know. If not, it's okay. We're not going to use it. But just in case, nobody's ever seen that symbol before?
Yeah, it's in the whole book.
Oh, it's in the book?
Yeah.
Oh, shit, I forgot. And or is like that?
Yeah.
Okay. So or looks like this. I like that symbol because it's like you or you, somebody freaking cleaned the room up. So it just goes through here. And looks like the letter A where the middle symbol, the middle bar just fell out, right?
Oh.
So it's kind of easy to remember. Okay, but again, I don't really necessarily use those too much, but there they are. I'll keep them over here, sorry. So what's that going to be? It's going to be 8 out of 80. So 0.1. I love it. Okay, sweet. Okay. So let's do this. Now we got enough information. We're going to create the formula for or. And then we got a little bit more to do to figure out the formula for and. Formula for and is going to be weird. Because how do you construct the fact that it's an intersection? How do you create that with in a formula form? It's easy to see visually, but the formula is going to be a little bit freaky. The or formula is going to be relatively easy. Did I bring markers that work? That would be amazing. Let's see if you guys have any power. Okay. Is this? I don't know if I'm doing it right. So, real quick, you guys, for this one. Ooh, that's really not good. Okay. N or under 20? I'll do U, N or U for under 20. Is that cool? What was this piece? What is that piece? 40 out of 80. Under 20. I like it. So this would be the probability of under 20 plus, what's this?
No.
The probability, somebody said no, right? Is that cool? Minus, what's this? Two. Good. No and under 20, because of course those are the people counted twice because they're in both groups. So that is that. Let me make it more general. Do you see how or is basically add? When I say that, does that make sense? Because you're going to hear me say that a few times. Or is basically add. Why do I say basically? Because there's a little adjustment if there's any overlap. You don't want to count people twice. Is this cool? So the most general way I could write this is the probability of A or B is probability of A plus probability of B minus the probability of A and B. That is the formula for OR. I like it. Okay. So here's our first little formula. You're going to see it several times, so if you can't quite see it, don't worry. All right. And is going to take a little bit of work. So we're going to get there.
Wait, so A and B means like together added?
No. Or means add.
Okay.
A and B means you have to be in both groups.
Like for that.
This is or.
No, at the end, like the subtraction of A and B.
Yeah, so this would be those that are in both groups. So there's two people that were in both groups. Both the no's and the under 20s.
Yeah.
Yeah. All right. Okay. So the math we've done so far, not very intense. Would you guys agree with me? Very, actually kind of mellow, right? We created a formula, but we actually didn't have to use it. We created it after we did stuff, which you're not used to. You're used to getting the formula, then you do stuff. Just to remind you guys, again, this specific problem, I give us, didn't we get a lot of information?
Yeah.
We got everything. We know everything. So that's why we don't need a formula. That's why it's a beautiful situation to create formulas. There are other situations where I don't give you anywhere near this much information, and then you're going to need the formulas, right? Okay. We're not going to do the formula for and yet because it's a little more involved. So what about this next idea? What's the probability that somebody said, I'm going to make this up, that somebody is under 20 given that they said yes. Okay, let's parse this out a bit. The probability they're under 20, the probability that they are under 20. Do we know that they're under 20? The probability. What is the probability that they're under 20? Do we know that they're under 20? No. It's asking me for the probability they're under 20, given that they said yes. So what do we know about the person? This is different. This problem is telling me something. No other problem told me any information. This one's giving me information. What do we know about this person?
They said yes.
They said yes. He said yes. No. Okay. Maybe? You guys are with me? Bless you. How many total people could this problem be talking about then?
40, 39,
What do we know about the person again? What do we know about the person? They said yes. How many people could we be talking about then? 39. You with me? Does that make sense? Because aren't we, this probability problem tells us the person they're looking at said yes. So I can throw everybody else out. I could throw everybody else is gone. This is my whole universe. So out of those 39 people, this sets up the bottom. Out of those 39 people, how many are under 20? 31. So anytime you have a given, your whole problem becomes smaller. You could throw out everything except what you know. And the biggest mistake is people think they know this. No, the probability they're under, I don't know if they're under 20 or not. This is the probability they're under 20, given they say, okay, I know this. I know they said yes. So can't I throw these people out? Not literally, but just throw these columns out, and then this is my universe now, right? So then I can just see 31 out of 39, beautiful. So givens are really nice. They're the only time that the bottom won't be the total, right? You have to give me information for the bottom to not be 80. If you don't tell me shit, it could be any of the 80 people. Is everybody with me? Okay, all right. And then what is that, just out of curiosity?
0.7949.
7949?
Yeah.
Okay. Did I? No, I didn't. Oh, by the way, let me ask you this. What's the probability somebody's under 20, just by itself? 40 out of 80. 0.5, right? 50%, right? Let me ask you this question. Do you notice how these are both questions about the probability someone's under 20? In this one, I just know more. Bless you. Does knowing they said yes change the probability that they're under 20? What was the probability that they're under 20 by itself? 50%, you with me? 50% chance, yes? If I know they said yes, does the probability that they're under 20 change? What is it now? It's almost freaking 80%. Yes? Didn't the chance that they're under 20 go way up? Could you guys, if I gave you a moment, do a little creative writing and figure out what question would lead to that? What question would under 20-year-olds say yes to a lot more than somebody who's over 20? I'm certain that we all could come up with some possible examples. No? I'm sure you could. It doesn't matter right now. Okay, I'm not going to change this into creative writing as much as part of me wants to. Okay. Let's do another given question. These get trippy, I understand. But notice the denominator is based on what's given. Why was it 39 here? Because I know they said yes. So I'm talking about 39 people. That's it. Right? Okay. Let's see. So let's do another given equation, given problem, and then we'll create the given equation, and then we'll create the and equation. Okay. So looking at this still, I don't know what number I'm on. Let's see, 6. What's the probability somebody said maybe? By the way, here, I'm not going to write the word given. I'm going to make this symbol. This symbol means given. It doesn't mean divided by. Again, I'm sorry. We just weren't around when they chose symbols. The symbol means given. Probably it said maybe, given that they're at least 20. Try to figure that out. Don't say anything. No, this one, yeah, okay, it doesn't matter. I did have an example different. Okay. This one you almost can't go wrong because, well, you can. Oh, what's the bottom gonna be?
4.
What is it you know about the person? Let's start there.
At least 20.
We're given that they're at least 20. So let me ask this question again. Yeah, it's gonna be 40, sorry. Let me go back. So out of those 40, how many said maybe? Yeah, 5 out of 40, 11. Which is 125, 11, 12.5%. So I ask you a similar question. What was the probability somebody said maybe just by itself? 15%. Did the probability change if I know they're at least 20? A little bit, yes? Would you then say, let me ask you this. Does the probability that somebody said maybe is it dependent on if I know what their, I'm sorry, what's probably, somebody said maybe, is it dependent on what age they are? So knowing that they're at least 20, did the probability change? What was the probability? I said maybe before, it was 15%. Is everybody with me on that? I said maybe it was 15%. What is it now? What did it become? What did the probability said maybe become now that we know they're at least 20? It became 12.5%. It went down a little bit, yes? So isn't it true that the probability that it said maybe is dependent on if they're at least 20 or not?
Yeah.
Totally. Kick ass. It's going to come back in a little bit. Okay. Just a little side note. Let's develop the formula for given. I told you, I warned you. It's a lot of talking today. Just the way this shit happens. Okay. Let's develop this way. It's going to be a little bit different than what we did before. I'm going to do something very strange that you would only see a math teacher do. What can I do with the fraction if I wanted to change the look of it? What can I do legally?
Reduce it. Or reduce it or flip it.
I can't flip it. That would totally change what the fraction represents. But I can reduce it, yes? I can either divide the top and bottom by the same thing or multiply the top and bottom by the same thing. And I can't do it with 0, correct? I can't divide or multiply by 0. So, watch this. Everybody say with it. I'm totally allowed to do that, correct? I could multiply top and bottom of a fraction by 11.739 if I felt like it. And you're like, go for it, math dude. So can't I divide top and bottom by 80? Does anybody disagree that that's the same number? When the 80s cancel, it's the same stupid number, right? So math doesn't give a shit. And you guys are all like, why? So here's why. Do you remember how we developed the formula before? I pointed out parts of what we did. Does anyone know what this is?
Probability of people who answered maybe. Probability of A.
Yes? Yes. Okay, so that's the probability of maybe and at least 20. Divided by, what's this one?
Probability of at least 20.
Probably of at least 20, right? Gotta use context clues to know that's this. So in general, the formula, why does it make sense the bottom is related to the given? Because that's how we built this. The bottom is related to the given, correct? Whatever information I know tells me what the denominator is gonna be, right? It's like earlier it was 39 because we knew they said yes. Here it was 40 because we knew they said they were at least 20. You guys all with me a little bit? And again, if we look back at the other given formula we did, we could do the same kind of thing. So here's what this looks like generally. The probability of A given B is the probability of A and B divided by the probability of B. And there's something I could have drawn earlier, but I'll draw it right now for this. Have you guys ever seen a picture like this before? That's not supposed to go outside of the universe. Okay. Have you guys ever seen a picture like this? You know what it's called? Venn diagram. I love it. Venn diagram. So if I know, what is this? Can somebody read this to me?
Probability of A given B.
Okay, so what do we know happened? What happened? What are we given happened?
B.
B. So whatever event B is, in this case it was being at least 20.
Yeah.
It could be rolling a 6. It could be finding a dragonfly. It could be stumbling over a rock and then finding a quarter that's face up. I don't know what to show. It could be any event I define, correct? Strangely specific. So doesn't it make sense then that if this happened, is this cool? Something in here happened for sure, because that's what I'm given. I'm given that B happened. What's the only way that A could have also happened? Where does it have to be?
In D.
In here. Could that happen? Nope. What about this guy? The only way that something in A could have also happened at the same time is if it's there. And what is this?
That's the overlap.
That is the and. Do you guys agree? That's where A and B both agree.
Uh-huh.
That's the things that are in both groups.
Yeah.
So that's why the formula visually makes sense. And it also makes sense algebraically, right? Okay. And you're like, that's not enough sense, Jeff. Okay, shit. Now, do we have a formula for OR? Let's collect our formulas. Let's see. Let me, all right. I don't need you anymore. Good job. Weird example. This board just needs to just lose some things. So we have a formula for OR, and we have a formula for given. I'm gonna write the formula for given two different ways. So the formula for OR, yeah, is basically addition. And it's got a little bit of an adjustment in case anybody got counted twice. Will I always count things twice? Will A and B ever be 0? What if I said the probability of a bowl of ice cream or a rock? Is there anything that is both a bowl of ice cream and a rock at the same time? Can you make ice cream look like a rock? All day long. Is it actually a freaking rock and ice cream at the same time? Right? You don't see geologists going, strawberry. Right? You with me? That'd be kind of cool if we could. But don't try it, kids. Get you in a lot of trouble. Okay. You guys kind of with me? So this can be 0 sometimes. So this is an adjustment for those situations where we accidentally counted some twice. But if you ignore that for a minute, it's the OR is just both of them added. Is that cool? Probably A or B is probably A plus probably B. You just have an adjustment sometimes. Okay, what about given? This is the and over the given. So let me write this two different ways. What's probably B given A then? Probably a B and A.
Over the probability of B.
A, there it is, the given, right? The idea in this problem is that the second dude is there and the two are anded, right? It's just a verb that noun. Or that's not a noun, what is it, conjunctive? Let's not make this English class, okay. So real quick, just a really just out of nowhere example. What's the probability of F given W? Given goes on the bottom, the two on the top anded. Yes, that's it. That's all that formula means. You guys all with me? I'm gonna take away the flip flops and whiskey. Just want to say that. Do you guys notice how both of these ways that I wrote it, they both have probability of A and B? I know I say B and A over there, but are books and alcohol different from alcohol and books? They're the same thing, correct? Tammy and Joe, Joe and Tammy. It's the same damn group of people, yes? Okay. Can't I, so what we're missing is the formula for and, correct? Can't I just freaking solve this for and? Why is probability of A and B not by itself? What's with it?
Yeah.
Probability of B, for example, right? Looking at this guy. Come on, guys. There's not a lot of algebra in here. There's a little bit. So here comes a little bit. Can you solve this for the and piece? What sucks about this equation, besides it exists? There's a fraction in it, correct?
I'll say just do it.
Yeah. I can kill any fraction in any equation in the universe. That's the one time I can kill fractions because I have two sides to balance what I'm doing. I'm supposed to bring balance. So how do I kill the fraction on this side? Multiply by P and B, right? Peanut butter. So what do I do the other side? Multiply by P and B. So then probability of A and B equals the probability of B times the probability of A given B. Can you see if I do the same thing with the other way to write it? I get a different formula for this. Oh man, I forgot to do it. Yeah, we'll do it now. How we all doing? Now, real quick, these two are a little bit silly because A and B could be anything, so they could actually just switch the meaning of them. That's one way to look at these two problems. But there actually is a really fundamental difference here. We'll get to it here in a minute. Do you notice, again, that's the adjustment piece. Do you guys all agree with me now? That's an adjustment piece. If I don't need it, then the or becomes just the straight addition, right? Or is addition. And is multiplication. The adjustment piece is this given piece. If I cover that, isn't that just PB times PA? Isn't that just PA times PB? Yes? Maybe? All right, give me a minute. It's going to make more sense, I promise. For just a second, I have to explain to you why it makes sense and is multiplication. I want this to make sense. And I meant to do this earlier and I forgot. Two quick things I could do. One of them is related to a traumatic experience from young Jeff's life. So that sounds fun. And the other one is, we'll see. All right. So let's say I want to join a fraternity, right? You guys all with me? And I really don't, obviously, especially not now. Not Will Ferrell, whatever that movie was. All right, so I want to join, and the funny thing about fraternities is that's one place in real life you see Greek letters in America, right? Lambda, Lambda Nu, and Sigma, 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 right? The Greek letters for fraternity, sororities. Okay, everybody with me? All right, I'm extra boring today. You guys are almost all asleep. So let's say I'm going to join this fraternity, and there's this hazing that they're going to do. Where I went to grad school got in trouble. One of the houses got in trouble. So the hazing here is not anything dangerous. I have to walk down this hallway, and every third step I take, somebody slaps me on this cheek. And every fifth step I take, somebody slaps me on this cheek. You with me? Okay. I like somebody got really worried about me. It's not happening. It's not real. So wouldn't you agree that there's a 1/3 chance I get slapped in this cheek? Because it's 1 out of every 3 steps. Is that cool? And there's a 1/5 chance I get slapped on that cheek, right? So how often will I get slapped on both cheeks? How often will that happen? I am awake. Bam, and then bam, and then bam. How often is that going to happen? How many steps? 1 out of 15. Does that make sense? 3, 6, 9, 12, 15 is the first place that it's 3 and 5 divisible. So that's the first place I'm going to hit both. So how did you get that? 1/3 times 1/5. Okay. Another situation that's a little more, that one's really kind of silly, which is fine. Let's see, I need somewhere to draw. I can do it over here. Do you guys, are you aware we used to have something called the space shuttle? And I, as a small child, this is going to be very surprising to you guys. I was a complete nerd and geek, and I was completely, totally into, a big surprise. I mean, I would sit in the corner playing with the calculator, and I was like, I wonder what the hell he's going to do. But I was really into the space shuttle, and I did my time. I mean, we lived in Florida for a little while. I did my time in Florida. And so sometimes we would go out as a school, go out and we'd watch the space shuttle. Or if I was home, we would just go to the end of our court and we could actually see it taking off. We weren't that close, but you could definitely see the smoke trail. You could see the sun glinting off of it. You could actually see the sun glinting off when the fuel tanks would come off. That was so cool. For some reason this day, we didn't go out. And some of you guys should know what I'm talking about, what it's leading up to, right? So I remember, I'll never forget, I was in English class, sitting right next to the door, because I, get the hell out of class. And we were taking turns reading this play, and I can see it in my mind. Over the loudspeaker, they come on and said, of course, it had blown up, right? So very traumatic for young Jeff, started crying. I was just inconsolable. Do you guys, first off, are you guys aware of this? Are you guys aware that's not the only time it blew up? Everybody, right? So the second time it blew up is because it lost too many heat shields on the way out. And so when they came back, they didn't have enough protection from the friction from the atmosphere, and it blew up. And they're still finding pieces to this day. It was just strewn across this huge swath of land, Texas and other states. The first time it blew up, do you guys, anybody know why the first time? This is such a fun day. Let's talk about horrible disasters. In the fuel line, there were these things called O-rings. They were basically valves to make sure the fuel went only one direction, and that sounds like a good thing, right? The fuel goes the other side, things can get very bad. You guys all agree with me? Why would they have multiple of them?
Failures.
Right? Same reason you would have multiple locks if you live in certain neighborhoods. Yes? I definitely lived in those neighborhoods, trust me, right? Going to grad school, I had to save money somehow, and you're just like, if I survive, this is going to be great. So the same reason you would, anybody ever set more than one alarm when the next morning they had to be up early and it was really important, you had a final at 7 or something. Those are always awesome.
Yeah.
Yes, you set multiple alarms, you said, hey, can you call me? I'm not going to be up, so, oh shit. All right. So you set multiple alarms. Why? Each one of those, you're doing it so that you have, yeah, exactly, backups, fail-safes, right? So obviously, let's say that this is an overstatement, obviously. Let's say there's a 1% chance that these things will fail. That's way higher than it really was. In normal conditions, a 1% chance of failure. If we treated this, so what's the only way that the people would be in trouble? If all of them failed. So that means this one fails, and this one fails, and this one fails. So if and meant add, I just increase the chances of them failing. 1% plus 1% plus. So obviously that's not what it means. So let's look at it this way. This one will fail 1 out of 100 times. Is everybody in agreement?
Mm-hmm.
Out of those times, how often will this one fail? 1 out of 100. Right? So one will fail 1 out of 100. The other one will fail 1% of those times. And out of those times, how often will this guy fail? 1 out of 100. This multiplies out to be 1 out of 1,000,000. Right? I like those odds. You can't make it 0, unfortunately. Most things you can't make 0, but you can make them really damn close to 0. Is everybody sort of with me? Now, so this is another indication of why and is multiplied, because if you multiply two numbers that are less than 1, the result becomes smaller. And what is and always doing? Less and less things can get in, right? It makes the answer smaller and smaller. Okay, so I want multiplication for and to make inherent sense, and addition for or to make sense. On that day, by the way, it got really cold, and we're talking about Florida, so that didn't really have to be that cold, but it got below freezing that morning, so the O-rings didn't work the way they're supposed to be. The material they were made out of wasn't really rated for that cold of a temperature, and they were just so cocky, because we had been up there like, you know how to do this shit, just send that thing up. So of course these failed because the probability of failure went way up because of the cold temperature. You guys all with me? So if you want to, you can search, space shuttle O-rings, blah, blah, blah. Anyway, so, okay. I don't know why I like to take myself back through that memory, but oh well. It's a good example of why we do this kind of thing and how it leads to multiplication for and.
Those rings held together the fuel?
They were basically valves to make sure that the fuel only flowed in one direction.
Oh.
So if they wanted to flow back, they couldn't, right? Okay. If the fuel wanted to flow the other way, it couldn't. Wait.
So that means that the fuel backflowed and ignited.
Yes, exactly. So of course, that's what happened. We saw what happened. Yeah. I think there was something. Wait. Something else I wanted to do. I can't remember now. So let's see real quick. We got. Oh yeah, that's what it was. Okay. Last thing for today, guys, and then we'll head out a little bit early. That means I get to head out early too. So I said earlier that this could be 0 sometimes, right? And of course, you can see that very easily. I used to use cat and dog, but then there was a cartoon cat dog or dog. It was cat dog, right?
Yeah.
Yeah. And you don't want to think about the biology of that poor creature for too long. So I stopped using cats and dogs, and now I use stuff like Bowler ice cream and rock. I haven't heard of that cartoon yet. Full of rock cream. I haven't heard of that one yet. So when the probability of A and B equals 0, we call that situation a certain name. What would it look like if I drew the Venn diagram and that's true?
It would be two separate circles.
Yeah. So the elements in A don't let the elements in B come into their circle and vice versa, correct? Both directions. So this name makes a little bit of sense. We call the situation mutually exclusive. So they both exclude each other. You can't come in here, and oh yeah, we can't go in there. They mutually exclude each other. So the probability of something being both is 0. So for example, the probability something is a motorcycle and a river. I was going to say hot air balloon, but then I was almost certain somebody here was going to be like, well, actually, if you hook this thing up and you do this thing, you have the exhaust shooting up and this way, and you fly over. All right, I'll stop. You guys with me? That probability is 0, right? Unless you're on a serious trip. Your motorcycle is not going to be a river. Okay. All right. There will be problems where the very first sentence in the problem is like E and L are mutually exclusive. And the mistake students make is they pass right past that first sentence and they start trying to do shit with the numbers they give you. That first sentence is everything. If I tell you event E could be elephants and event L, lollipops. If those are mutually exclusive, what does that mean I can write down mathematically?
E, A, and B equals 0.
The probability of E and L equals 0. So any formula I've got to use for that problem, if E and L shows up in there, I can put a 0 there. If you skip that first sentence, you're screwed. You don't have enough information. And that's where I get people, I don't know what I'm supposed to do with this. Don't skip the first sentence. Okay, here comes another thing. So that's one idea, is mutually exclusive, and it's related to this. So if A and B are mutually exclusive, do you see how the formula becomes that?
Mm-hmm.
So in that one case, you could just add the two event probabilities together to get the or between them. Maybe. Okay. The other thing has to do with this equation. So the adjustment was this term. All right. Oh, that's right. We got one more thing to do after this. So I probably lied to you, but too bad. This guy is the adjustment term. So here's this idea. If the probability of A given B, and real quick, what does this mean? What has happened in this statement? What do I know has happened? B, good. Whatever the hell B is. B could be what? It could be any event you can imagine. Somebody having long hair. Somebody rolling a 5 on a die. Somebody flipping a tail. Somebody's car breaking down. Whatever. It could be any freaking event. We know it happened. If B happens and A does not care, what does that mean? So if an event happens and the other event's chances don't change at all, wouldn't you say that that means it didn't give a shit? So if some random person who lives in a totally different place, if they wake up late for class tomorrow, will that affect your car starting tomorrow morning?
No.
Those are independent of each other, correct?
Yes.
Now, what I love is everything I'm saying could be a creative writing exercise where you can imagine some string of events. Right? It's really difficult in real life to have any two things truly independent, and then you can start talking about quantum mechanics and all that shit, but let's not do that. Let's not do it. So if the probability of A given B is the same as what the probability of A was to begin with, so doesn't that say A doesn't give a shit about B? B happened. Did A care? Nope. It's just trucking along, doing its own thing. Hey man, look at this. All right, whatever. All right. So B happened, A stayed the same. If that is true, we call A and B independent. If this is not true, they are dependent. So again, in a homework problem, the first sentence is going to say, J and W are independent. You stop and you write what? So J and W, independent. You can write two different things. J given W equals, good, J didn't give a shit, W happened. Or you can also write, yeah, if they're independent from each other, they each don't give a shit about each other. That sounds terrible, right? And some of you guys are like, I know math is like that. Let me be quiet. Okay, maybe. Yes, I'm sorry. You had a question.
Can you give an example of when two things would be independent?
Totally. Okay, here we go. It's almost like I placed you there. Sure, we'll use you. Substrate board. How well do you guys know cards? How many suits are in a deck of cards? 4. Yeah, everybody know that. Okay. So we have hearts, diamonds, spades, and clubs, right? And balloons. No, it's Lucky Charms. How many of each? 13. Making how many total? 52. What are the cards themselves? Let's do aces low. So ace, 2, 3, up to 10, jack, queen, king. And that's repeated for every single one. So there's a 10 of spades. There's a king of diamonds, blah, blah, blah. I'm almost certain everybody in here at least we're not going to suddenly start playing no holds, no limit. No, Texas, whatever the shit. You can tell I play a lot. No limit, not kidding. So, if I ask you this, I pick one card, what's the probability I pick a king? Yeah, how many kings? 4. Out of how many cards? 52. Is everybody with me?
Yeah.
Real quick, let's do something we haven't done yet. What does that reduce to? 1 out of 13, 11. Now, what's the probability I pick a king given that I picked a club? So what's the bottom going to be now? What's the bottom going to be now?
13.
13, because it's clubs. I know clubs happened. There's 13 of those. And how many out of those clubs are kings?
1.
1 is a king of clubs, yes. That's okay. Are these different? So are king and club, are they dependent or are they independent? Independent, because if club happens, does the probability of king change? No. Why? Because I threw out 3/4 of the deck, and I also threw out 3/4 of the king. So my chances of a king happening did not change. It didn't give a shit. It's like, okay, I don't care. Now, real quick, what's the probability I pick a king given that I pick a face card? Oh shit, how many face cards are there? Jack, queen, king have faces on them. There's 3 in each suit, so there's how many total? 12. Out of those 12 cards, how many are kings? 4. So are king and face card dependent or independent? What was the probability of king before? 1 out of 13. What's the probability of the king if I know that somebody picked a face card? 1/3. So if I pick a card from a deck of cards and I say, what's the probability this is a king? Your answer is 1 out of 13, right? Or whatever that decimal is. You with me? If I say, oh yeah, by the way, this card is a club, did that help you at all? No, it's still a 1 out of 13 chance. If I say instead, oh yeah, this card is a face, it's a face card. Now your chances have gone way the shit up to 1/3. That is a huge jump up, right? If you're putting money on this being a king, you're really happy with what I just said. Are you with me? Does it make any sense? Does that help back there?
Yeah.
So that's a real life example, sort of real life, because cards is still not really real life. In real life, very few things are truly independent. But there are definitely things that are independent. Okay. What was the other thing? Oh yeah. Unfortunately, there's one more thing. So I got you and me really excited, but we're almost done. Let me think. Oh yeah, okay. If I pick, so let's do this old standard problem. 4 red poker chips, 6 blue, and 10 green. Everybody with me? I have a really exciting, everybody just stay calm. In the hat, I've got 4 red poker chips, 6 blue, 10 green, correct? Let's do a really quick little, everybody get in the same field of thought. Let's probably pick a blue if I pick 1.
6 out of 20.
6 out of 20, which is? Right, because you multiply by 5 to make it out of 100. Is that cool? It doesn't matter. Okay. Everybody with me? That's nice. I can ask you blah, 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 blah. What if I pick 2 chips? I can do this in 2 ways. So I'm gonna first do it, let's just go straight to this. I do it without replacement. What does that mean? I could either do it with replacement where I pick 1 and then I drop it back in and then I pick 1. So it's possible to get the same one. Are you guys with me?
Mm-hmm.
So this time I'm gonna pick 1, I'm gonna feed it to my little brother, and then I'm gonna go pick another one, right? Or throw it away, whatever. Sorry, Jim, explained so much.
590.
Now, so watch this. I pick 2 without replacement. Let's probably get a blue and then a green. So it's probably I reach in and I pick out a blue.
6 out of 20.
6 out of 20.
1019.
And I throw that away, right? And means, or means add, and means multiply. And then a green, let's probably pick a green now.
10 out of
10 out of 19, right? Because I lost a chip, correct? Now, real quick, isn't this formula supposed to be probability, remember the and? Probability of blue times the probability of green given blue, correct? Green, given that I picked a blue, doesn't that explain why this is different? Given that I picked a blue and threw it away, the probability is green changed, didn't it? Are you with me? Okay. And then whatever the shit that is, I don't know. I don't know. It's about 16, let's say 16.9%. I don't know. I'm making shit up. Somebody save me from myself.
Wait, why is it
1.5 times about 3/20. Maybe I'm very wrong. It's point. It's the other way. Is it the other way? I don't know. Somebody help me. Nobody's gonna help me. Nobody can multiply that. Go ahead. Are you guys understanding that example?
Oh.
I don't want to. Nobody's gonna help me. Okay. You can't tell me this.
1578.
1578. Okay. I went the wrong. Watch this now. Another example with without replacement. What about green and then green? Green and then green. So what I normally do is I have 2 things I want to pick, correct? So I do like a little hangman game. One thing times another thing. Let's probably get a green first.
10 out of 20.
10 out of 20. Throw that away. Let's probably get a green next.
10 out of 20.
No? 1 less green, 1 less chip, because I'm still throwing it away, right? 1 less green chip, because didn't I throw that first one away? And then 1 less chip. Why didn't this top change for green? Because I didn't pick a green. I still have all 10 greens in there. Do you guys see that? All right, good. And then whatever the hell that is, I will still care. And then the real final problem, look, I'm letting this out way early, so I don't want to hear about it. If I pick with replacement, meaning I put the damn chip back in. So that means when I put it back in, everything resets, correct? So what if I want to know that, B and then G? So probably, good Lord, Jeff. Today's been a long day.
6 out of 20.
The probability I get a blue, 6 out of 20, and I drop it back in the bag,
10 out of 20.
10 out of 20. Do you see how now, oops, probability of B and G is probably B times probability of G given B? But y is this equal to the probability of g? Well, if I put the first one back in, does it matter what I picked? If I put the first chip back in,
No.
this doesn't matter. Do you see how they're independent then?
Yeah.
So if I do it with replacement, all the things reset, they're all independent. If I don't do it with replacement, every probability changes, a totally dependent situation. What if I had picked 5 chips? B, G, GR, B. Wouldn't I just have more fractions? Do you see, I can just extend this kind of problem out? That's plenty, guys. All right. We'll leave a little early today. Don't get used to it. If you have any questions on your test, or you didn't get your test back, or anything, just come and see me. I'll see you guys Wednesday.
It was regarding that problem. It says